So for our second climb up the factoring mountain, the first thing we want to do is expose one kind of quadratic factoring process that's not like the others that we've seen. Actually, we're going to do that a couple of times. And that's going to be what we call the method for factoring a difference of two squares. Difference of perfect squares. And this is a method that I think we talked about briefly earlier in the semester, but I want to again call it out one more time because it's one of these types of problems that doesn't look like it fits the mold of something that we know what to do with, even if it actually does. So here's an example of a problem that might be in this area. Suppose that I ask you to factor 64 minus 9a squared. So right off the bat, this doesn't look like something that we would know how to factor using the methods that we talked about in our first climb up the factoring mountain. Because if we try to hit this with greatest common factor methods, well, 64 and 9 turn out to have nothing in common. And one of these terms has variables in it, the other one's a constant, so there's no variable factor in common either. So greatest common factor doesn't help us. It also doesn't look like our methods for factoring trinomials are going to help us either because there aren't three terms. There's only two. So we tend to fall into a habit of thinking about these examples as their own separate category. Even if we can approach them using the same kind of analytical method with a factoring box that I like so dearly, that we have approached other types of problems. So here's how I like to think of these. I want to take my 64, and I want to take my minus 9a squared. And I'm going to put those into these two boxes here on the diagonal with the goal of then breaking those apart. So what's some way that I can factor out 64? What are some pairs of factors that multiply together to give me 64? That's a pretty long list, it turns out. So before we start thinking haphazardly about it, let's also take a look ahead. And my look ahead is that whatever factorization that I propose here, when I multiply it all back out and combine the like terms, the two terms that reside in these boxes need to cancel one another out. Because in the final answer here, if we work backwards, right, we don't have a third term that's unlike these two. That's a part of our original problem. So whatever goes in these two boxes needs to cancel one another out. I'm just going to kind of write that here. That's going to be our goal, is that these two need to cancel. And one of the best ways that we can ensure that those two do cancel is to try and break apart these two terms using equal factors, by which I mean, how do I break apart 64 into something times itself? 8 times 8. So that's where this method gets the name difference of perfect squares. Each of these two original terms happens to be a perfect square. 64 happens to be a perfect square of the number 8. And this is convenient because now whatever I get in this box is going to be 8 times something, and whatever I get in this box is also going to be 8 times something. So that's going to make it easier for us to ensure that the two terms in these boxes are equal and opposite, so that they cancel one another out. All right, so what about the minus 9a squared part? If I'm following the same kind of pattern, how can I break this apart into something times something, where those somethings are the same as one another? I'm not saying that very well. Let's start with the a squared part. How can I break apart an a squared in my factorization? Yeah, same way we always do, as an a times an a. That's going to account for my a squared. What about 9? Same method, right? 3 and 3. And so now I've accounted for the a squared, I've accounted for the 9, but I haven't accounted for the negative out in the front. So how do I make it so when I multiply these two things together I get a negative? Yeah, make one of the two of them negative. If I make them both negative, I'm going to get positive 9a squared in this box. So I need to make one negative, the other positive. So we started with these two things that were perfect squares, and we broke them both apart as perfect squares. 64 broke into an 8 and an 8. 9a squared broke into a 3a and a 3a. And then I just needed one of those to be negative to account for this negative sign. Let's verify that when I do the checking part, remember that's the nice thing about these factoring grids, is that the checking is kind of built in for us. When we do the checking part and we work backwards, that those two terms do indeed cancel one another out. So what is 8 times 3a going to give me in this box? 24a. And then 8 times negative 3a in this box, negative 24a. And sure enough, if I were to multiply this back out and combine those two terms, they would cancel, which is what we wanted. Right? So we've gotten the factorization that we were looking for. What does it look like in our final answer? Each of my binomials begins with an 8. It ends with a 3a. And the only difference between my two binomials is that one of them has a plus in it and the other has a minus. So 8 plus 3a times 8 minus 3a is how we can factor this difference of two perfect squares. And I find that the hardest part about using this method is remembering to use it. The actual application of it is less problematic. So what's going to be your cue? When you look at a problem in which this would be useful, how are we going to know that this method is useful? Where does the difference part show up in our original question? It shows up because we're subtracting these two terms, right? That's what difference is a synonym here for subtraction. And then perfect squares, that's the other thing that makes this method work as well as it does, right? 64 happens to be a perfect square, 8 and 8. 9 happens to be a perfect square, 3 and 3. A squared is also a perfect square, a and a. So in order for this method to work, both of our terms in my difference need to themselves be perfect squares of something. In this example, they were perfect squares respectively of 8 and of 3a. And so it's no accident that all of the terms in my factorization were 8s and 3a's. The only difference being that one of them is the sum of them and the other is the difference of them. And it's because those terms were the same in these two binomials that we were able to get the cancellation that we need in order that the product, when we FOIL it back out, only has two terms at the end of the day. Now let's go to the intermediate level. And unlike with many intermediate levels, I feel like this is probably the most advanced single technique that we're going to do in all of factoring. And the only reason it's not the advanced level is at the advanced level, what we're going to do is see problems that require us to use all of the different tools in our toolbox together. Right? So this is the last sort of step to learn one individual new method, and then the advanced level is going to be to put all of them together at once. So at the intermediate level, what we can do is factor a quadratic trinomial. And that's just like our last intermediate method. The difference is that now the leading coefficient is not necessarily equal to 1. Leading coefficient not equal to 1. So here our example is going to be the polynomial 3y squared minus 4y minus 20. And we say that the leading coefficient is not equal to 1 because this 3 right here is the leading coefficient. That's the coefficient that's attached to the square term, right, the quadratic term. And so the issue now, the reason that we don't already have the tools to factor this expression, if we go and try and use our factoring box, which we're going to do again, but if we just try to use it the same way that we used it before, what we'd be confronted with right away, 3y squared minus 20, is that when we break apart the 3y squared, it's no longer as simple as just a y and a y. Right? Now that 3 has to be accounted for somewhere. Luckily for us, there's only one way to break apart a 3 into a 3 and a 1. Right? But the issue is that the presence of this 3 right here outside of my factoring grid is going to confound our sum and product game, right? The game that we play where we say, we just need a pair of numbers that multiply together to give me negative 20 and which add together to give me, in this example, negative 4. Right? Well, the problem is that that's not going to work anymore because this square right here is not going to come across as itself. It's going to come across as 3 times itself. Right? So this 3 is going to gets in here and it stirs things up so they don't work as cleanly as they did when the leading coefficient was 1. So we need a new approach to this. We want to still be able to use the sum and product game in some way, but in order to get there, we just have to add one little step to the process. And this is the part where I have to confess that I never learned how to do this when I was first an algebra student. I didn't learn it in high school, I didn't learn it in college, never learned it in graduate school, never learned it for probably the first 3 or 4 years of being a college math professor. And I wish I had. I spent so much time trying to factor these polynomials in other less efficient guess and check kind of ways. And it was just awful. So I didn't like these kinds of polynomials. But it was in the process of teaching this course that I was introduced to this method. And ever since then, I love it. It's just almost like, it's like math magic. So here's how it works. It's called the AC method. And the good part about the AC method is that it lets us use the same game, the same skill as we used before, which was find a pair of numbers which multiply together to give me something, and that same pair of numbers also needs to add together to give me something. Right, so it's the same game that we're already used to playing. The difference, actually let me start with what's the same about both. The thing that's the same about the AC method compared to the method we learned before for quadratic trinomials is that the sum, the thing that we need our numbers to add to, is still just the middle term. It's -4 in this example. So this is what we sometimes call the B coefficient. We'll definitely call it that when we talk about the quadratic formula next Monday. This is the coefficient of the first power term. But what goes here is not just -20 as it would have been when we factored monic leading coefficient 1 trinomials. Instead, what I want to do is multiply together that coefficient with the A being the leading coefficient. So this number here is not -20, it's going to be 3 times -20. So let me try and indicate that that's what we're doing here. So I'm going to take my 3, and I'm going to take my -20, and I'm going to multiply them together. So that's going to give me -60. So what I want is I want a pair of numbers which multiply together to give me -60, but which add together to give me -4. The pair of numbers which works here is -10 and 6. And if we get there, we've won most of the battle, right, in this. So we can check that -10 times 6 is indeed -60, and -10 plus 6 is indeed -4. And they call it the AC method because of multiplying these two coefficients together, the A coefficient and the C coefficient. That's how we got this process started. So now the question is, how do we use the A and the C in this method? And so here's how we end up using the A and the C. What we're going to do is take them, and into my factoring grid, I'm going to place -10y and 6y in these two cells. That's going to work because, two reasons, really. The first reason, so I'm going to port this over here, -10y and 6y. The first reason is that if I were to add up all the terms in my factoring grid now, I would indeed get back 3y squared minus 4y minus 20. So what this game over here has let us discover is how to split apart this middle term in a way that's actually going to work for the rest of our factorization. And you'll see why the rest of what the other reason is that this works in just a minute. Because our goal now is we just have to figure out how to fill in this entry and that entry in my factorization grid. 3y plus what and y plus what. In other words, at this point, we've partially figured out a factorization in that we know it's going to be 3y and y. And whatever we pair the 3y and the y with have to multiply together to give me these two middle terms. The good part is we have these two entries on the outside already. So to find the others, we're just going to chase around the table. If I want to know what this entry is, I need to know what to multiply 3y by in order to get 6y. What do you think? What's the missing factor here? 2. And so what that's doing is it's arguing that one of my factors is y plus 2. Great. Now to find my second factor, I can do it from two different angles. I can either say what's missing between y and minus 10y, or I can say what's missing between 2 and negative 20. Right? And those two answers need to be the same answer. And the AC method's genius is that doing this over here to split the middle term ensures that those two answers are the same. Whatever number I fill in here has to work with y to make negative 10y, and it also has to work with 2 to give me negative 10. What is that number? Negative 10. You can check that both of those work. And now I have my factorization. So 3y minus 10 times y plus 2. So this is our first application of the AC method. I want to do one more example that shows one more little wrinkle that exists in the process. So here's a new example where the leading coefficient is again not 1, the leading coefficient is 4. And the reason that this example is a little bit different is that now there's not only one way to break apart that 4, that leading coefficient. We could break it apart into 4 times 1, or we could break it apart into 2 times 2. And so as we don't have to do guessing and checking on this, let's use the AC method in a slightly different fashion than we used it a minute ago. And this time, we're going to jump straight into the AC portion of the evening. So the first thing we'll do is multiply the A coefficient by the C coefficient. 4 times negative 6 is going to give me negative 24. And so negative 24 is going to be the thing that we want to find two numbers that multiply together to. And then that same pair of numbers has to add together to give me 5. So what pair of numbers is going to win the sum and product game for this sum and this product? Negative 3 and positive 8. Great. That multiplies together to give me negative 24, and it also adds together to give me 5. So that's the pair that we want. And we're going to take that negative 3 and that 8, and just like we did in the last example, we're going to use those to break apart my middle term, meaning I'm going to put negative 3x into one of these boxes and positive 8x into the other. So that's how our middle term has split apart. Now the difference between this example and the one that we just did is now I don't have a 4x and a 1x or a 2x and a 2x. I don't have those terms out here to get me started. So now we're going to do something new to get that process started. And the something new, it's not really that new. In fact, it's a callback to things that we already know. This happens every time we climb these mountains, right? Is I'm just going to pick one row, or we could use one column, it doesn't really matter. I'm just going to say pick the first row of this table and ask, what is the greatest common factor between 4x squared and minus 3x? X, exactly. The 4 and the 3 have nothing that they share, but the powers of x, again, picking the smaller of the two exponents, I'm going to pick x to the power 1. And so what these most have in common is x. And so that's how I'm going to get my process started. Because as soon as I have one of these squares filled in, now the rest is going to snowball. Because now I can play the game of, well, what's the missing factor between x and minus 3x? Negative 3. And what's the missing factor between negative 3 and negative 6? Negative 3 times what equals negative 6? Positive 2. And then finally, what's the missing factor between positive 2 and 8x? 4x. So see, as soon as we get one of these entries on the outside, the rest we just have to play the missing factor game to figure out the others. And now we have our factorization into 4x minus 3 times x plus 2. And that's the AC method in all of its glory. So our last step up the factoring mountain is not a new technique. It's just the combination, the culmination of all the techniques that we've learned up until this point. Use multiple factoring methods within a single problem. One problem. So here's what that might look like. And then we'll just take sort of a 40,000-foot view of what a solution might look like. So let's suppose that my interest is in factoring. So this method starts with another trinomial, but it's not a quadratic trinomial this time. Right? Our highest exponent goes all the way up to 4. So before we even think about the methods that we know for how to handle quadratics, we should probably start at the foot of our first mountain by thinking about the first factoring method that we should ever think about using. What's the low-hanging fruit? How can I start my ball rolling by factoring something out of this expression to make it a little simpler to handle? First step in any factoring workflow. Yeah, very good. First thing is to think about the greatest common factor that exists in all three of the terms, and you said you think the greatest common factor is 4y squared. And I agree. So 4 is the largest number that is a common factor of 12, 44, and 40. And y squared is chosen here because it's the least exponent on all my powers of y. So 4y squared indeed goes evenly into all three of these terms. So the first step for us is to bring that 4y squared out and then figure out what's left. The missing factor between 4y squared and 40y squared is 10. I'm going to skip the grid on this part of the problem. Between 4y squared and 44y cubed is plus 11y. And between 4y squared and 12y to the fourth is 3y squared. The greatest common factor should always be the first thing that you think about doing in a factoring problem. In the previous couple examples that we did, it wouldn't have helped us. But in this example, it's essential for us to do that step first, because without it, we don't have a quadratic trinomial to factor. But now that we bring that 4y squared out, we do. This trinomial in green is quadratic. It has the highest power 2. And so now that the greatest common factor method is done, these three terms in green have nothing in common. And so now is the time to employ one of our other methods. So how do you think we should factor 3y squared plus 11y plus 10? What technique should I use there? As this is a quadratic trinomial whose leading coefficient, 3, is not equal to 1, that means we have no choice but to use the method that we just learned today, the AC method. So let's plug that in, and then that will bring us home here, both figuratively and literally, because it's the last thing we'll do today. So we need a pair of numbers which multiply together to give me something and which add together to give me something. What should they add together to give us, first of all? What should the sum equal? That's always going to be this middle coefficient, 11, the b coefficient. So they have to add together to give me 11, but they also need to multiply together to give me, this is where the AC from the AC method comes in. What does their product have to be? Three times 10, 30. So I need a pair of numbers which multiply to 30 and add to 11. What pair of numbers works? How about 5 and 6? Yeah. 6 and 5, 5 and 6, again, it doesn't matter. The only difference is which of the terms we write in the upper right and the lower left. And it won't matter. Your final answer won't care. So we'll use the results of that game that we just played to split apart our middle term into a 5x and a 6x. Then we have our other terms, 3y squared and 10. And now to get our AC method started, we'll start by picking any row or any column and bringing out the greatest common factor. What's the greatest common factor between 3y? Oops, I screwed up my variable here. It's 5y and 6y. What's the greatest common factor between 3y squared and 5y going to be? That's going to be just a plain y, right? So there's the GCF of that. And now we just start the missing factor game. Missing factor between y and 5y is 5. The missing factor between 5 and 10, 2. And the missing factor between 2 and 6y, 3y. And now that we've chased all those factors around, we have finished completely factoring this expression. And the last recommendation I'm going to make to you is don't forget this original GCF in your final answer. Sometimes, again, after doing all of this, people take a victory lap and they just write down 3y plus 5 times y plus 2. Don't be so quick, right? Take a victory lap, but then also remember that the 4y squared that you found in the first part of the problem is still a part of your final answer. So 4y squared times the product of 3y squared plus, 3y plus 5 times y plus 2. I'm running out of room here. There we go. And the moral of the story here is that in any factoring problem where you have to use multiple steps, the first step you should be thinking about is always the greatest common factor. Right? Get that done and out of the way first, because it can only make your factoring task simpler from there. There's a chance that it doesn't do anything for you, as in all of our previous examples, but if it does, it's going to give you an easier factoring problem to work with than you otherwise would have had. Even though in this example it only gets us down to something that still requires us to use the AC method, at least it gets us there, because without it we don't have a quadratic, and all the rest of our factoring methods are predicated on having a quadratic to factor.